Hello and welcome to Add-on. So today in this video, we are going to learn about the linear particle accelerator, also known as the LAQ. So have you ever wondered how scientists give tiny particles enough energy to smash into each other at nearly the speed of light? Well, one way is through a linear particle accelerator, also known as LAQ. So we are going to understand this LAQ step by step. So first thing first, what exactly is this LAQ? So think of it as a particle racetrack, but instead of looping around, it goes in a straight line. This accelerator uses alternating electric fields to speed up particles, which are usually ions. So it is designed for nuclear experiment, unlike electrostatic accelerators. So it's not like your everyday static electricity experiment. It's a powerful electromagnetic accelerator. So let's talk about its construction first. A LAQ is made up of several metallic hollow cylinders or tubes, kind of like a row of, soda cans, one after another with spaces in between. So let's understand this by the diagram. Each cylinder is connected to an alternating current or AC power source, which changes its polarity with each cycle. Now here's a question for you. Why do you think that they use an alternating current instead of direct current? Yes, the answer is alternating current allows the direction of the electric field to keep switching. So each gap between the tubes can give our particle a push forward. This setup allows continuous acceleration without the need for insanely high voltages. Right. So here is where our journey begins, the ion source. This is where charged particles like, protons or ions are first generated. Imagine we are accelerating a positively charged ion like proton. It enters the first gap where it's attracted to the negative charge of the first tube. The alternating current source is tying so that when the ion reaches the gap between the first and the second tube becomes negatively charged, giving it another boost of acceleration. So here's a quick question. Have you ever noticed that when something is moving faster, they cover more distance? Well, the same thing happens here. Now, each time the ion enters a new gap, it picks up more and more speed. But here is a trick. Because it's moving faster each time, we need to make sure it still reaches each gap right as the field is reversing and pulling it forward again. And that's where the length of the tubes comes into play. Now, let's break down the math a bit. Don't worry, I'll keep it simple. So when our ion crosses one gap to the next, it gains energy from the voltage across each gap. After the first gap, its speed is V1, which we can calculate using the energy formula, which is half mv1 square equals to qv, where m is the particle's mass, q is its charge, v is the voltage applied, and after rearranging the equation, we have v1 equals to root over 2qv by m. Great. So that's our speed after the first acceleration. Now when it hits the second gap, it picks up even more energy, almost twice as much as before. So our speed after the second gap becomes v2. v2 is equals to root over 2 multiplied by root over 2 qv by m. And now what is this root over 2 qv by m? It's v1. So we can write v2 equals to root over 2 multiplied by v1. Now, if the speed increases like this, what should happen to the length of each tube to match this increase? Right. Each tube has to get a little longer to accommodate the increased speed of the particle. So that way, the particle arrives at the end of each tube just as the field changes, giving it another boost. So to keep everything synchronized, we set the length of the tube in the proportion 1 is to root over 2 is to root over 3, and so on. It goes like root over 4, root over 5, and so on and so forth. So if the first tube is 1 unit long, then the next should be root over 2 units long, and the next should be root over 3 units long, and so forth. This way, the particles spend just the right amount of time in each tube to keep up with the alternating electric field. It's just like timing your steps in an escalator. If you go too fast, you may overshoot, and if you go too slow, you miss the steps. But with the right timing, you are in perfect sync. So that's the secret behind, LINACs or the linear particle accelerator. So by arranging the tubes in just the right lengths and using alternating fields, we can make particles reach incredibly high speeds. This precise acceleration technique is what makes LINACs so valuable for research in nuclear physics, medicine, and many more areas. So, what do you think? If we wanted to double the speed of this ion, how much longer would each tube need to be? Give it a thought and let's keep learning about the incredible physics behind particle accelerators. Thanks for joining.